Our first speaker is Léon Kuchenbecker. He's a bioinformatician by training, did his PhD in immunoinformatics at the Charité. And we're lucky to have him as the technical lead for software integration at GHGA, and we'll talk about the technology stack. Léon.
Thanks, Julien, for the kind introduction. And yeah, welcome back from the coffee break. Let me check if this works. Yes, it does. So as Julien said, I'm going to talk about our technical stack, basically how GHGA works under the hood, give you some ideas of what features are currently out there. As Ollie already mentioned, we have launched something in August, and we are very proud of that, and it can do certain things, and I would like to advertise these things and give you some pointers to our posters, and yeah, transport some understanding of what we have achieved. I would like to start by recapitulating a bit the basic requirements or what we wanted to achieve originally. One obvious thing that I think all agree we want to do is provide an infrastructure where researchers can securely exchange sensitive, in the sense of person-related research data that is pretty large. We also want to enable fair data management of this research data. So these researchers should not only in secrecy exchange this data through our platform, but the data should be visible, discoverable. It should be stored for a long period of time to enable secondary use, to enable reproducibility of previous research. We, from the beginning, were clear that we wanted to do this not as a single institution, but as a federation, as a consortium of institutions. And we wanted to build a technology stack that runs on the premises of these partner institutions. And lastly, we don't only want to build a federation, we also want to be part of a larger federation. So we committed to operate the German node of the federated European Genome-Phenome Archive. So coming from this requirements, we started thinking about technical solutions, and one of the most consequential and early decisions that we took was that we would build a custom technology stack to deliver these goals, and not to piggyback on other initiatives or try to put together existing solutions, because we had the resources to really build a solution that would feed into the national specific requirements and environments, like the national networks, like accommodating things like the Modellvorhaben, genome sequencing, and other things. But of course, we don't want to reinvent the wheel, and we already heard about things like the Global Alliance for Genomics and Health, developing standards, making sure these things can be interoperable. So we also were clear that we wanted to explore and use existing tools and standards wherever possible. Another decision that we took was that we wanted to build a state-of-the-art cloud-native software architecture. And to some of you, that may sound a bit contradictory to the fact that I said we want to run on the premises of our partners. But in fact, these partners and the German bioinformatics communities and institutions in Germany actually run quite a few on-premise clouds. So this was actually also a good standard to define, or an interface to define on how we would bring tools to infrastructure if needed. And secondly, it keeps us also agnostic to running on these premises. So we can, in principle, also move things to the public cloud or parts to the public cloud in the future. And the last aspect on this slide, and another important pillar of what we do, is our strong focus on security. So we depend very much on the trust of the public, of the institutions that submit data to us. So having a strong focus on security is really something that guides us on all the different layers of designing the application, thinking of how we want to build this, what should be the architecture to actually building it, testing it properly when we develop, and also how we operate it in the end on the infrastructure and how that can be properly secured. So having started with these general thoughts, I would like to present to you in a nutshell or on a very high level of the architecture that we have come up with and how GHGA works. Ollie has already touched some of these things on the higher level. So you've already heard there's GHGA Central, aka the German Cancer Research Center, which is also the contractual partner for our data submitters, so the research data controllers. And at GHGA Central, we run our service backend. And The service backend at Central is then connected to the data hubs, which run object storage. And this can come in different flavors, but the common denominator that we agreed upon is that this object storage should provide an S3 API, which is an industry standard developed by Amazon, but also offered as a compatibility layer in many on-premise object storage solution, commercial ones, open source ones, and so on and so forth. So when you look at the data, we have the encrypted research data, so all the heavy lifting on the I/O and storage happening at the object storages of the data hub. And at GHGA Central, we run the logic, the compute at the moment, solely in Central, and we store the research data encryption keys and the non-personal metadata. The non-personal metadata is basically what we can use for discovery of this research data, so everything that describes the data and can be shared with the general public. When we zoom into this central service backend, which is really the heart of what we are developing, we are following what is called a microservice architecture. So we compartmentalize our task of building a software, and instead of building one large monolith of software, we build many different individual small pieces of software, each of which have a very well scoped task. And these services, they deliver the functionality of GHGA service backend together, but they should be as decoupled as possible. So ideally, they don't even know of each other's existence. There are many advantages to such a pattern. There are also challenges, but there are advantages on the development side, like when you develop such a software. But there are also one obvious example is that you can nicely scale these individual components independently from each other. So when there's like one service that is, for example, doing heavy lifting on data, like QC on FASTQ files, you can replicate this service and scale it up, and other services that just handle 500 bytes of JSON per hour or whatever, they can stay small on the scaling level. These microservices, they can be completely stateless. So they just get sort of some task from the network and they do something and then they report something back to the network. Or they can have a memory, so they persist information. And if they do so, we rely on MongoDB, which is a NoSQL database standard. Since these services are designed to be decoupled, there's no sharing of databases between services. If a service has a database, then it has its own database. And besides MongoDB, we use what is called HashiCorp Vault, which is a special storage engine for storing highly sensitive information. And that's where we put the encryption keys of the research data. These services also have to communicate with each other naturally. And if you want to really keep this decoupling as high as possible, then the go-to architecture when you want to design communication between microservices is asynchronous communication through a message broker. So basically, a service just publishes messages to what is called topics, and other services can subscribe to these topics when they're interested and consume this information and act upon it. But the sender of the message doesn't even know who reads the message. There's really no coupling on that front between the services, which can make developing them individually and independently much easier. We use a message broker, also a fairly popular choice, Apache Kafka, in our system. And sometimes we also break from that rule. So sometimes there's really synchronous communication on the REST API between such services. That means they talk synchronously to each other. And in that case, for example, in some security critical scenarios, where we really want to make sure if we want to revoke access for something that all the other service really has confirmed, okay, I have revoked access, then this is, we sometimes deviate from this pattern. Naturally, in that case, the services have to know of each other's existence and have a bit of a contract between them, how they talk to each other. This is the service backend in a nutshell, basically. This is how it talks to itself, how it persists information, but of course there's also communication to the outside world. And we don't only develop microservices, we also develop tools that run elsewhere. So we have a web front end that I guess most of you have already seen and played around with. We have CLI applications, and they don't run at the GHGA central infrastructure, but they run elsewhere in the user's infrastructure, in the general public, or the internet. And when they have to talk to the service backend, they do so through what is called an API gateway. So there's basically one surface to the public that exposes an HTTP API. And this API gateway then selectively routes individual requests to individual microservices, as some of them sort of are responsible for serving to external requests and others are not. The user-facing programs, they also interface directly with the storage at the data hubs. So when there's an upload or a download, then the user-facing tool will directly communicate with the data hubs S3 storage. The data hubs typically also secure these storages behind things like API gateways / reverse proxies or other security infrastructure as the data hub's security concept dictates. But they are connected to the internet and they can serve requests from the public internet and from our user-facing tools. They don't do this just arbitrarily, but this process is brokered by the microservice backend. So the backend also talks to the S3 storages and regulates access to things. So for example, the backend can go to the Tübingen data hub, say, give me a short-lived URL for a user to access a certain data, and then that is given to the backend hands it to the user-facing tool, and then the user-facing tool contacts the storage backend. But it's important to know that the data, the heavy lifting data, does not first go to central and then to the user, but there's a direct connection happening. So that's basically the architecture in a nutshell. I will stop here. Of course, that omits a lot of detail, but I think should transport like a general idea of how our software architecture looks like. Of course, there's quite some complexity in this microservice deployment. There's a lot of third-party components and other things that are needed, and that adds complexity to how you can actually run such an application. It's not something that you just start program and then GHGA is running. But because of the microservice architecture, because of the cloud native architecture, because of the third-party tools like Kafka and MongoDB, there's quite an overhead in operating and deploying such an operation, such an application. And we use a Kubernetes cluster at GHGA Central for this task, which is a popular so-called container orchestrator. So this manages basically the deployments of these containerized applications, both of our own microservices, but also the third-party components like Kafka, like MongoDB, and other things that are needed to run this thing. We have a strong focus on GitOps and infrastructure as code. That means whatever we do when we manage infrastructure, when we create or design infrastructure, when we describe which service versions we want to have running on our infrastructure, we describe this in formal languages and manage these descriptions in Git repositories. So like this, we have reproducibility of these steps. We have version history and all of the beauties of properly managing these steps. And we also have a fully automated test deployment pipeline that a developer can go and describe a new deployment with a new service version that they want to try in conjunction with other services. And then the system will automatically spawn this and say, here, you have an internal deployment that you can play around with. Another key thought in this context is zero trust philosophy. We try to make as little assumptions about the security of our surrounding infrastructure. So we don't trust internal networks, or we try to keep access rights for credentials as well defined and as minimal as possible. All network traffic, as I said, is encrypted even between microservices. Everything, there's no trust sort of in even our own virtual networks. Yeah, this is how our deployment stack looks like. In brief, the dark green blocks are things that we consume, but are managed by other units, either DKFZ or by the data hubs in case of the S3 object storage. And then we really stack our applications in light green on top, like a Kubernetes cluster, like our microservices, third-party software, and this is then managed by the GHGA team. Another thing that I would like to mention is that really we stepped up the quality of what we're doing when we made the transition from being in a development mentality to going into production, is having comprehensive internal documentation when it comes to describing this infrastructure, being aware of all the components that you have in this infrastructure. So we have a really large asset registry of software components we are managing, keeping track of who has access to these systems in production, and how are secrets being managed, who has access to these secrets, and so on and so forth. If you're interested in this automated deployments and how we manage deployment, visit our DevOps poster. Some of you might already have done that, but it's out there in the poster gallery. The next thing I would like to briefly touch is describe or give you an idea of how we do software development, what kind of mode we have converged to when changing things about the GHGA data portal, service backend components, and so on and so forth. One beauty about this microservice architecture is that you can really do a lot of things independent from each other in the early development process. So we have maybe a sub-team working on things that are related to file services that do S3 management. people working on authentication, authorization, metadata management, but also the DevOps utilities and deployment infrastructure as code things, the front end, and so on and so forth. So a component can be a microservice, it can be a scope of microservices that work tightly together. And here in this stage, when these components are changing and features are being added, development is really high performance also on the time scale. And also testing can happen to some degree with the components in isolation. So the component can test some degree of its functionality just by itself. This can happen in highly in parallel. Then comes a point in time when we say, okay, we want to bring the new features together and integrate them to a overall functionality. And the first thing that we do is what we call offline integration tests. So we have a test suite in which, again, we code tests that test all these different components in combination. They go through our user journeys in an automated fashion, talk to the APIs of the individual microservices, and check if these functionalities work as expected. As I said, this is codified, and some of them are actually written using BDD in natural human language and then translated into functions. And this is executed offline in the sense that the tester runs this locally on their machine, deploys all the microservices and all the backend and everything and runs it locally. If that checks out, we bring the new components to the infrastructure, to a testing environment in the infrastructure. So there's some infrastructure integration step where we update a test environment to the new versions of components, bring new components that haven't existed before, and then rerun our test suite, the same code that we have run locally, again, on the real infrastructure with the Kubernetes cluster, with the other third-party tools. If that also checks out, we run manual integration tests. That means the tester will then follow a certain script and go through the UI and also check if these journeys work out when you execute them manually, because we currently don't have automated UI tests, and this sort of catches the last bits of errors on the outermost layers of the application. If it was a major change and not just a fix or something, if a new feature was brought in, we ask the team for feedback and say, okay, guys, we have a new deployment internally. Go play around with it, assume any role, be a data submitter, be a data steward, and see if these things check out from your perspective. And if they also give a thumbs up, we bring the new software to our production environment. If you're interested in our testing strategies, there's also a dedicated poster on that you can check out outside. Okay, that wraps up the why and how, and brings me to the what we have done, what is currently out there, what is in the GHGA production release 1.0, so to say. One product or feature I would like to highlight is our authentication, authorization, and identity management. Already for quite a while, we have made the decision that we would rely on life science login as an OIDC provider. I guess most of you have, one way or the other, gotten in touch. There are so many websites that enable you to log in with your institutional credentials. They rely on such an IDP federation like Life Science Login. And so we have basically outsourced the primary authentication to Life Science Login, so people can log in with their institutional credentials. What we have recently added is multi-tier security on top of the Life Science Login process. So we now have a second authentication factor that is entirely managed by the GHGA data portal, which works based on TOTP and makes sure that even if there is a breach on the life science side, even if you lost your credentials and so on and so forth, people will not be able to log into GHGA with your credentials. And we have an identity verification system. Ollie already mentioned this earlier, so we can now tie privileges in the system, for example, access to a data set or being a data steward or whatever privilege you have, it is being tied to an independent contact address that has to be verified beforehand. It can be a phone number, can be a postal address or anything that works independent from your Life Science login. So it shouldn't be an email address that you can log in with your institutional credentials to. And that really gives us a solid ground on the security of being sure that the right person is granted access and that if they lose access to their account, no harm is being done. This whole authentication authorization process we already heard about the Global Alliance earlier is also Visa and Passport ready. We have not fully adapted the standard because it is, as of now, not mature enough to suit our needs, and the integration and Life Science login is not complete. but we have adopted the standard to whichever degree possible internally so that we can migrate to the standard as soon as we also can use it. On this topic, we have 2 posters, authentication authorization, two-factor ID management. Check them out if you like. The next feature I would like to touch is research data management. I already mentioned earlier, we have the central component and all these individual S3 storages. So we have components that can orchestrate and manage this federation of S3 storages. They manage the up and download process, issuing pre-signed URLs through the S3 API, delivering them to the user locally so that they can download and upload data directly to the storages so that this is as performant as possible. The data is Crypt4GH encrypted at all times, so both doing transport, but also at rest in our systems. It is always Crypt4GH encrypted, and the encryption keys are securely stored and managed through our service backend and the HashiCorp Vault database. We currently feature a secure and user-friendly access management and download process. We are lacking some components on the submission process. So currently submission is a bit tedious and manual, but the download and access management process is really user-friendly and fully functional. So users can go to the data portal, request access. These access requests can be managed in a data steward portal. And if approved, the user has a very convenient way of obtaining the data from the data portal. If you want to know more how this works, there is a storage and sharing poster as well. The last feature I would like to mention is the framework for metadata handling. We call it metadata or METL data. This enables us to execute transformation workflows on metadata. So the non-personal metadata that is used for discovery of the data, for seeing the data in our data portal. So the metadata model that you also hear about a lot and see posters about, this is really our ingress model. So the model that we think is best suited to sort of interview our customers of what has happened to the data before it was being generated, or what has happened experimentally before the data was generated. But it's not necessarily the ideal model for presenting the data set, for discovering the data set, or interfacing with central EGA and so on and so forth. So we have query-specific artifacts that are being generated by these workflows from the original submission data, while always maintaining as an archive the original state of the metadata as it was submitted to us. We have utilities that make working with the metadata user-friendly. So we have a model-agnostic spreadsheet to JSON transpiler, so you can fill our official Excel sheets instead of writing JSON or YAML, and then it will be transpiled to our official JSON format. And we have a data validator that enables users to check whether metadata is compliant with our ingress model. Again, there's a poster. So if you're interested in metadata and the ETL processes around it, check out the corresponding poster. There would be many more components and features to talk about. I guess that would burst the timeline here. I think the UI, the web UI, of course, we have some UI development, is one of the most visible pieces. Here you see the authentication process through 2-stage life science login, two-factor authentication. Here you can see how people can manage validated contact addresses in their profiles. So there's a lot of things to discover, but I think since this component is most visible by itself, I'm not giving a detailed description in this context. Okay, so that's what we have and what we can do and what is out in production for a couple of weeks now, and we are really happy the system is running stably. It's all the fuzz that naturally happens before you launch such a product was definitely worth it, and we are in a good state of having that system up and running. So the question is, what are we doing right now and what we'll be doing the next couple of months? And we have acquired a bit of technical debt before going into production, things that we put back and said we would do them later. And one thing that's happening right now is actually a re-implementation of our front end. For various reasons, the code base hasn't aged very well. It's hard to maintain and to bring new features in it. And we have front end developers who are quite skilled in the Angular framework. So we also decided to switch frameworks. So we are re-implementing our UI at the moment. And secondly, we are refactoring our metadata framework from LinkML to SchemaPack. LinkML used to be the framework in which we describe our metadata model and the tooling that we use to work with metadata. But that gave us a really bad headache over time, especially the tooling, but also the standard solves actually many more problems than what we are having. So that's why we decided to develop our own solution, which is much slimmer and tailor-made to our use case, called Schema Pack. Again, there's a poster on this latest development if you want to learn more about that. Beyond managing technical debt, of course, we're also very hungry to bring new features and move the abilities that users have on our portal forward. So the next steps will be that we want to enable metadata model and metadata lifecycle management. Currently, both are assumed to be static in the portal, which is, of course, not true, especially as time progresses. So we want to be able to manage an evolving metadata model, and we also want to enable users to report corrected metadata to us and manage that lifecycle of these things. We want to complete the data submission portal, and in the context of that, separate a bit the business metadata from the scientific metadata. Currently, all of that is crammed a bit in our Ingress model, which is not really suitable for what we're trying to achieve. We want to technically connect to federated EGA. As already mentioned, we have signed the contracts, we are legally connected. We're now in the process of clarifying, okay, how does accession number generation work? How does the data flow go, and so on and so forth. And lastly, another keyword that you have heard already a couple times today, we want to enable users to no longer have to transfer the data, duplicate the data out of our infrastructure into theirs, but enable them to execute research on our infrastructure. So enable users to perform analyses in GHGA trusted research environments. And that closes my outlook. I would like to say a big thank you to the technical team who have contributed to this. It's great fun to work with you, and I think we can all be very proud of what we have achieved and what is out there right now. And yeah, thank you for your attention, and I'm happy to take questions.